Hello everyone, welcome back, and today also let us try to learn some more interesting things about the structure of atom. Now, according to Bohr's model of atom, electrons are supposed to move around the nucleus in fixed circular paths like this, and these circular paths they have fixed radius as well as energy. But according to the Heisenberg's uncertainty principle, it is not possible to measure exactly the position as well as momentum of a microscopic particle like an electron with absolute certainty. So now we cannot imagine an electron moving around the nucleus in fixed paths like this. Also, from the dual nature of particles, we have seen that electrons have particle as well as a wave nature. So if they have particle nature only, then the path of the electron can be like this with fixed radius, and the path can be fixed like this. But since electrons have wave nature also, their path cannot be fixed like this, because if they move as waves, they will be moving like this with wavelengths. So now this concept of orbitals, the orbitals are the fixed circular paths around the nucleus where electrons move. This concept of orbitals has been replaced by the concept of orbitals. The fixed paths around the nucleus with fixed radius and energy where the electrons move are called as orbits. Since the Heisenberg's uncertainty principle and the dual nature of matter were discovered later on, were proposed later on only after the Bohr's model was proposed. Only after these developments, the concept of orbitals which were proposed in Bohr's model, the concept of orbits which were proposed in Bohr's model have now been replaced by orbitals. Now, orbitals, these are defined as regions around the nucleus, regions like this, where probability of finding electrons is maximum. Orbits are the fixed paths with fixed radius in fixed energies where the electrons were supposed to move according to Bohr's model. But orbitals are regions, not fixed paths, but they are regions around the nucleus where probability of finding electrons is maximum. Now, taking into account these new developments like the Heisenberg's uncertainty principle as well as the dual nature of matter, a new model of the atom was developed, and this new model of atom is called as the quantum mechanical model of atom. Now, the main features of this model, the first feature is that the energy of electrons in atoms is quantized. Energy of the electrons in atoms is quantized. That means the electrons in atoms can have only certain fixed values under certain conditions. The second feature is that it considers the wave-like particles of electrons, whereas in Bohr's model, particle-like nature of electrons was considered. In this quantum mechanical model, the wave-like properties of electrons is considered. Then the third feature is that it emphasizes the path, that the path of an electron in an atom can never be known accurately. This follows from Heisenberg's uncertainty principle, which states that it is not possible to determine simultaneously both position as well as momentum of a small microscopic particle like an electron with accuracy. The fourth feature is that an atomic orbital is described by a wave function psi. This wave function psi describes the atomic orbital. Probability of finding an electron at a point within an atom is proportional to the square of the orbital wave function. Square of the wave function, that is psi square. So the wave function psi in itself does not have any physical meaning or significance, but its square, that is psi square, measures the probability of finding an electron at a point within an atom. So from the value of psi square at different points within an atom, it is possible to predict the region around the nucleus where electrons will most probably be found. These are the main features of the quantum mechanical model of the atom. Now, an atom can have a lot of orbitals also. And these orbitals, they differ in size, they differ in shape, as well as in orientations around the nucleus inside the atom. So to specify or to describe these orbitals, we need a set of 4 numbers, and these numbers are called as quantum numbers. So these quantum numbers, they are a set of 4 numbers which are required to specify orbitals in an atom. And as I said, we have 4 numbers. One is called as the principal quantum number. Now the principal quantum number, it is represented by n. Principal quantum number, it specifies or it determines the main energy level or the shell to which the electrons belong or the orbital belongs. It also determines the shape, the size, not the shape, the size and the energy of the orbitals. So principal quantum number specifies 3 things about the orbitals: the shell, the principal shell to which it belongs, the size of the orbital, and the energy of the orbital. Now, this number, the principal quantum number specified by n, can have values starting from 1, 2, 3, and so on. So, if for an orbital n is 1, the principal quantum number is 1, that means it belongs to the first shell. If n is 2, that means the orbital belongs to the second shell, and so on. Now, the first shell is called as the K shell, second shell is called as the L shell, then M, fourth shell, N, and so on. So, once again, if the orbital, for an orbital n is 1, that means it belongs to the first shell or the K shell. If n is 2, it means it belongs to the second shell or the L shell, and so on. The next quantum number is the azimuthal quantum number. This is represented by L. The azimuthal quantum number, it defines the 3-dimensional shape of the orbital. Principal quantum number specifies the shape, the size, and azimuthal quantum number, it specifies the 3-dimensional shape of the orbital. And L, the azimuthal quantum number, can have values starting from 0 up to n minus 1, 1 less than the value of n. So if n is 1, if the principal quantum number is 1, then L can have only one value, that is 0. If n is 2, the principal quantum number is 2, then L can have values starting from 0 up to 1 less than the value of n. n is 2, 1 less than the value of n is 1. So L can have 2 values, that is 0 and 1. Again, if n is 3, then L will be 0, 1 up to 2. So L can have values starting from 0 up to 1 less than the value of n. The next quantum number is the magnetic quantum number. Magnetic quantum number represented by m. Now this quantum number, it specifies the orientation of the orbitals, in which directions the orbitals are oriented, or in how many directions the orbitals are oriented. That is specified by this magnetic quantum number. Now m can have values starting from minus L through 0 to plus L. From minus L through 0 up to plus L. So let us see how we can obtain the values of m. If n is 1, L can be 0 only. So if L is 0, m can be 0 only, because m can have values from minus L, that will give us minus 0, through 0, that is 0, to plus L, plus 0 again. So m can have only one value, that is 0 only. But if n is 2, then L can be 0 or 1. Then m, for L equal to 0, m can be 0 only. For L equal to 0, m can be 0 only. For L equal to 1, m can be from minus L through 0 to plus L. So from minus 1 through 0 to plus 1. So m can have 3 values. Likewise, for n equal to 3, L can have values from 0 up to 2. For L0, m can be 0 only. For L1, m can be minus 1, 0, or plus 1. Here we have L up to 2. So for L2, m can have values from minus 2 through 0 up to plus 2. So in the case of an orbital where L is 2, m can have these 5 different values from minus 2 to plus 2. The fourth quantum number is called as the spin quantum number. Spin quantum number represented by S. Now, this quantum number, it specifies the spin of the electrons. The electrons, just like the Earth rotates on its own axis, it goes around the Sun, it also spins on its own axis, which is called as rotation. Now, just like that, electrons, they go around the nucleus. At the same time, they have a spin of their own. They can spin on their own axis also. Now they can rotate either towards the right, that is clockwise direction, or towards the left, that is anti-clockwise direction. The spin quantum number, it specifies in which the direction the electron is spinning. So this spin quantum number can have only 2 values, either plus 1 by 2 or minus 1 by 2. If the electron is spinning towards the right, that means in the clockwise direction, the value of the spin quantum number is will be plus 1 by 2. If it is spinning in the opposite direction, in anti-clockwise direction, then value of S will be minus 1 by 2. Now there are some very important points to remember regarding this quantum number. So let us see them one by one. Each shell consists of one or more subshells, and the number of subshells in a principal shell is equal to the value of n. So if n is 1, we see that L can be 0 only. Number of shell is 1. Number of subshell also 1. N equal to 2, L can be 0 and 1. N 2, value of n is 2, number of subshells is 2, having values 0 and 1. Again, n 3, L can be 0, 1 up to 2. Because L can have values starting from 0 up to 1 less than the value of n. Likewise, if n is 4, L will be 0, 1, 2 up to 3. So if value of n is 3, number of subshells is 3. If value of n is 4, number of subshells is 4. So here, each shell consists of one or more subshells, and the number of subshell in a principal shell is equal to the value of n. If value of n is 4, number of subshells 4. If n is 3, number of subshells 3, and so on. Subshells corresponding to different values of L are represented by the following symbols. If L is 0, it is called as the S subshell. If L is 1, then P subshell. If it is 2, D. If it is 3, F. If it is 4, G. If it is 5, H, and so on. So these are the designations that are given to different orbitals in an atom. If value of L is 0, it will be called as S subshell. If L is 1, P subshell, and so on. Now, there are 2 L plus 1 orbitals of each type in a subshell. 2 L plus 1 orbitals of each type in a subshell. For example, 1 is orbital, then L equal to 0. 3 orbitals, when L is 1. 5 orbitals when L is 2. What do you understand from this? There are 2 L plus 1 orbitals of each type in a subshell. So if L is 0, that means the S orbital or S subshell, 2L plus 1 will give us 2 into L0. So 2 into 0 plus 1. This will give us only 1. So each subshell will have only one orbital, which is called as the 1s orbital. If L is 1, it is called as the S subshell. Let us see how many orbitals it can have. 2L plus 1 will give us 2 into, in this case, L is 1. So 2 into 1 plus 1, that gives us 3. L equal to 1 means the P subshell, and the P subshell can have 3 orbitals, which are called as Px, Py, and Pz orbitals. Likewise, if L is 2, then we will get 2 into 2 plus 1, that is 5. L2 means the D subshell. D subshell therefore will have 5 orbitals, which are called as the 5D orbitals. So let us continue this in the next class.